discharge. I'm not going to go to the global lightning activity, which we discussed, but we're going to get to the real implication of a specific kind of lightning discharge, and then I'm going to talk a little bit about other relatively new phenomena discovered 20, 25 years ago, which constitute my present research interest, and I'm going to share with you raw data which I would like you to analyze and maybe help me in my research. It's not very complicated. We will do this either today or tomorrow using a plainly available image processing software that is available for free download. I'm not sure if I hope we can download it to your personal computers here, and then I'm going to upload a file or send you by email, and then you can look at the data yourself and try to find these mysterious phenomena which I'm going to talk about related to lightning. I'm trying to build up your expectations. So lightning. Lightning is generated in specific types of clouds. Not every cloud every day generates lightning, only a very specific, unique family of clouds, which we call cumulonimbus clouds, or meteorologists use the name CB. Usually they write for short CB, like this. Okay? And it's a very tall cloud base, the lower part, as we discussed yesterday, always a straight line at the lifting condensation level, the height of which depends on the relative humidity profile and the temperature profile, but usually 500 meters, 300 meters above the ground. And some of the pictures you sent yesterday show that the clouds are extremely low. However, cloud top can be extremely high, 12, 15, and maybe 18 kilometers. So sometimes those clouds are that well developed vertically that they can penetrate into the lower stratosphere. It's like punching through the tropopause, through the upper layer of the troposphere and into the stratosphere. And it looks like a big mushroom cloud, even similar to a nuclear kind of shaped cloud. They're very violent. You don't want to fly inside such a cloud because you have, as I will show you, very strong upwards motion and downwards motion of rain and hail and turbulence, and of course lightning. And the temperature in the upper part is obviously below zero, sometimes minus 20, minus 30. They can reach sometimes even minus 70. I will show you satellite images of storm systems where you can clearly see and easily identify where those monsters occur. I call them monsters not in a bad way, but they're big, scary animals. And they are not very long-lived. They live 1 hour on average, a little bit more, a little less. They have this very stereotypic kind of evolutionary cycle where they reach maturity and then decay and disappear. And during the middle period of their development, those clouds are a very efficient charge generation machine. They produce electricity, and the single storm can produce enough electricity that can suffice to provide the electrical need of a small town. Well, not maybe a small town in India, but a small town in my country. But this is a hugely effective natural machine that produces electricity. And those clouds, when you look from space, for example, this is from the International Space Station. So we're looking up from 420 kilometers, oblique way. Actually, astronaut takes a camera, goes to the window, takes a shot. This is an area that can cover from South Mumbai all the way up to North Mumbai, just one cloud. Huge area. And all this area is susceptible to the effects of lightning, hail, rain, flash flood, downdraft, high-speed winds, which can have effect sometimes unexpected, as we will see tomorrow and maybe on Friday, related to the dynamics. So when we look at a thunderstorm and try to assess its electrical structure, what we find by doing repeated measurements, and they are hard to do, I will show you that sometimes it's almost impossible to do a measurement within a thunderstorm. You have to be a little bit crazy to take an airplane and go inside, yet it was done. NASA did this several times, sending pilots right into the center of the storm, into the center of the cloud, in order to measure charge distribution and to evaluate what is the structure of the charge inside a thunderstorm that produces so much lightning. And as we've seen, lightning has a lot of electrical current. It can reach 20, 30,000 amperes, easy. I'm researching a certain class of really high energy lightning called supervolts. They are 100 to 200 and maybe even higher thousand amperes. So huge amount of current. Of course, they are the most dangerous ones because they can kill you in an instant if you are unlucky enough to be hit by lightning. So what research shows, and this had been verified many times over, that clouds are essentially big batteries with a negative pole in the center of the cloud and a major positive pole on the upper part. Negative and positive. This is like a schematic drawing. And when the cloud is mature and starts raining, and we have hail and downwinds, then appears a third positive charge at the bottom part. Okay? And from basic electrostatics, we know that if we have two opposite polarity charge centers, between those poles, there's an electric field, a potential difference. And as the amount of charge accumulates in the thunderstorm, the electric field grows and grows and grows until it's so huge that eventually the air breaks electrically and becomes a conductive substance. And there is a short, how do you say in electricity, you get this electrical short between the positive and the negative, and a current flows. And this is what lighting is all about. So it's an electrical kind of shorting, not a physical metal conductor, but the air is becoming conducting. And it gets hot, and as I said, expands and produces the thunder and the light that we see as lightning. I will give more details. But basically what I want you to visualize is that whenever you see those clouds, think of them as huge electrical machines with a minus at the center, a plus on top, and some positive charge carried by drops and ice particles that are slowly going to the to the ground. Different countries, different climatic regimes, different electrical structures. So basically what we see is that no matter where you are on the planet, be it summer or winter, the basic structure remains the same. It's just the volume is different. So in Florida, in summer, or in India, summer thunderstorms, monsoon type lightning activity, this is the structure. That you get the negative charge center in the middle of the thunderstorm, where the temperature on average is below zero, between 0 and -20. In the upper part, you will get the positive charge, and when it starts to rain, you will get this positive charge at the bottom. Okay? In the Mediterranean and in Japan, these are winter storms. So the atmosphere, to begin with, is colder and much more stable, and so you don't get those 18 kilometers tall cloud. They are usually 10 kilometers, maybe 12 in some rare events, and in Japan they're even smaller. But basically you see the same electrical structure, only it's more compact, much lower and more compact. And so this is the general structure of thunderstorms anywhere in the world. The only difference is, as I said, is what is the height of the cloud base, what is the height of the cloud top, and how big are the volumes that the cloud contain. Okay, and of course, in each type of thunderstorm, either summer, monsoon type, or winter type, there are specific attributes to the lightning activity. It's not the same. It's different. And as I will show you soon. So, this is what we call a mature thunderstorm. This is based on many, many balloon measurements conducted in the United States by scientists. This is Mary Beth Stolzenberg and her team. And they did repeated balloon launches with instruments. They would go to see where a thunderstorm is developing, go below it, and send a balloon with this device that can measure the charge, the temperature, the electric field. And when they published this paper, it was obvious that this naive perception of a battery is really too simple. Nature is not that simple that it has plus, minus, and maybe additional plus. Nature is complex, and it's changing all the time. The structure is different at the beginning of the storm, and as the storm matures, the cloud is a complete, I wouldn't say mess, but mixture of positive charge, negative charge, again positive, like a sandwich, a multi-layered charge sandwich. And in every location where charges are big enough such that the field, the electric field created is large, then the air may break down and lead to the generation of lightning. So lightning can appear between this negative charge and this positive charge and go down, or it can be formed between this and the upper part, or it can be formed here in the upper layer of the cloud, and it will change as the cloud matures and evolves. So this is a typical kind of cumulonimbus cloud. Remember this shape and the general electrical structure. And now you may ask, but how is this evolving, and how does it separate those charges? Why do we have certain areas and certain altitude where you have positive charge and areas that you have negative charge? How come charge is separated? So it's a big, valid kind of question, which I will answer shortly. There's a basic definition between the types of storms that we see. So so this is the three types: winter, ordinary, and super hailstorm, big animals. The big, strong thunderstorms, which I will show you shortly. So the flash rate is how many flashes per minute does this cloud generate. Why is my battery running low? I thought I unplugged in. Everything is working. I don't know. It worries me a little bit. Stand by just a minute. I'm sorry. Can you please have her come in? I think I have a problem. There's, I don't know, it shows that my battery is going down, but the charge looks okay. So there is a charger, everything is okay. It's working. I should plug in a different place. Maybe different. No, still no power. I don't know.
Only once you start.